What changed this week is that reinforcement learning is moving beyond right or wrong rewards into richer, more controllable training signals that actually shape reasoning. Instead of squeezing everything down to a final answer bit, these methods exploit traces, verifiers, and composable environments to push credit assignment earlier, generate fresh tasks on demand, and train on harder structure rather than stale benchmarks. That matters because it's the difference between models that memorize solutions and models that generalize under pressure. Here's what the new evidence says about where reasoning training is heading next. Let's explore the first paper, Reinforcement Learning from Rich Feedback with Distributional Dagger. Reinforcement learning from rich feedback with distributional dagger, or DIST-IL, argues that the standard RLVR recipe in reasoning models wastes execution traces, critiques, and ground truth solutions by reducing supervision to a terminal correctness bit. The paper, from the University of Southern California, proves two failure modes for prior on-policy self-distillation methods, such as SDPO and OPSD. F-divergence objectives, like reverse KL and Jensen-Shannon, do not guarantee monotonic policy improvement, and token-wise local gradients can miss delayed credit assignment with a two-step example where local updates converge to reward 1/3 while full sequence-level gradients reach 2/5. DIST-IL replaces that recipe with a distributional dagger-style forward cross-entropy objective that can query black box teachers and propagates future teacher-student disagreement back to earlier tokens. Under a local realizability condition, a natural gradient step improves expected reward by eta delta plus O eta 2, and the online variant achieves a regret-bound scaling as ON -1,4 for stochastic teachers or ON -1,2 when teacher variance is low. Empirically, on Cycno Evo L3, DIST-IL raises Quinn 3, 8, B, average, best at 16 from 73 to 76.1, and OMO 3, 7, B. Instruct from 68.8 to 71.9 at 5 hours. On LiveCodeBench V6, it reaches accuracy, AVG at 160, 656, and score, AVG at 160, 482, versus SDPO's 0.643 and 0.467, and on 738 hard math problems, it improves Quinn 3, 4B, AIM 25, AVG at 16 from 51.5 to 55.3, and Quinn 3, 8B from 69.7 to 71.1. Let's explore the second paper, Tron Targeted Rule, Verifiable Online Environments for Visual Reasoning RL. Tron, from the University of Georgia, reframes visual reasoning reinforcement learning as training on online, rule-verifiable environments instead of static VQA corpora. The paper introduces 520 generator verifier programs grouped into 5 ability buckets: spatial, mathematical, diagram, pattern, logic, and counting each with a 0-9 difficulty ladder that can stream fresh image question rollouts on demand and return exact rewards without an LLM judge. A model-free audit over 8,320 probes reports 99.07% generation success. 502 of 520 environments graded A, and a difficulty curve on Quinn 3, VL 4B. Instruct that drops from 72.8% pass rate at level 0 to 41.3% at level 9, confirming that the curriculum axis is real rather than nominal. Using DAPL-style RL on Quinn 3, VL 4B, instruct. Quinn 2, 5, VL 7B, instruct, and MIMO VL 7B, SFT, Tron improves mean accuracy on 10 external multimodal reasoning benchmarks from 52.61 to 55.23, 40.85 to 43.35, and 63.37 to 66.5 respectively. The specialist analysis shows that capability transfer matters more than visual format alone. A math specialist gains +20 on Helix Maze, and a diagram specialist gains +10 on Puzzle VQA Rect Height, but the visually aligned specialist wins only 1 of 10 benchmarks. So robust transfer comes from covering the underlying reasoning operations, not just matching the surface modality. Let's explore the third paper. Verifiable environments are Lego bricks recursive composition for reasoning generalization. This paper introduces RACEs, short for Recursive Automated Composition for Environment Scaling, a framework for reinforcement learning with verifiable environments that treats each environment like a Lego brick. If one environment's output type matches another's input type, They can be recursively composed into new executable tasks. Races standardizes environments as a four-tuple of input sampler, deterministic mapper, natural language descriptor, and verifier. Then instantiates four operators: sequential, parallel, is very sort, and select to induce different reasoning behaviors such as state carryover, multi-thread tracking, order recovery, and distractor discrimination. The authors build a pool of 300 environments and train Qwen3, 14B, and DeepSeek R1 Distill Qwen 14B with GRPO on 32 times. NVIDIA A180GB GPUs using 12,800 training instances for 300 steps. On 6 unseen benchmarks, Races improves DeepSeek R1 Distill Qwen 14B from 48.2 to 51.3 average score, and Qwen3 14B from 58.8 to 61.1, with notable gains on IFEvol, Longbench, V2, Enigmata, Live Code Bench, and AMI. The method is also more sample efficient. Using only 50 base environments, Races reaches 50.8 on Qwen3 4B. Instruct 2507, surpassing individual environment RL trained on 300 environments at 50.4, while deeper compositions show a non-monotonic difficulty curve with best average performance at composition size 5. The key result is that compositional structure, not just more isolated tasks, produces stronger reasoning generalization. That's a wrap on today's AI paper highlights. Thanks for watching.